Imagine standing outside on the night of September 2nd, 1859. The sky above you explodes with color. Curtains of red, green, and violet light ripple and dance across the heavens with such intensity that the night seems transformed into an eerie twilight. In the Rocky Mountains of Colorado, gold miners jolt awake, convinced that morning has arrived hours ahead of schedule. They stoke their campfires, fry bacon, and brew coffee under the glow of auroras so bright they illuminate the landscape like daylight. In towns across New England, ordinary citizens step out of their homes and read newspapers by the light of the northern lights alone, no lantern required. Farther south, reports stream in from places where such displays had never been seen before. Cuba, Hawaii, southern Japan, parts of China, New Zealand, and even near the equator in Colombia. The entire planet appears to be wrapped in a shimmering, otherworldly veil of light. At the same time, in telegraph offices scattered across North America and Europe, chaos is unfolding. Operators stare in disbelief as their equipment suddenly comes alive with sparks and crackling sounds. Some receive sharp electric shocks that knock them back from their stations. In multiple documented cases, paper records and wooden components ignite from the surges racing through the wires. Telegraph lines that form the backbone of long-distance communication, spanning thousands of miles, begin to fail spectacularly. Yet on one particular line connecting Boston, Massachusetts to Portland, Maine, something even more astonishing occurs. Two operators continue exchanging messages even after they have completely disconnected their batteries. The power driving their conversation comes directly from the storm itself, an invisible force generated by the Earth's disturbed magnetic field, interacting with the atmosphere. This is the Carrington Event, the most powerful geomagnetic storm in recorded human history, and every detail presented here is drawn from verifiable contemporary accounts, scientific observations, and historical records. Welcome to this documentary-style exploration on a channel dedicated to uncovering hidden chapters of true history and the mysteries that still echo into our present day. We focus exclusively on events that can be cross-checked through primary sources, newspaper reports, scientific journals, and established research. If you appreciate stories that blend meticulous historical accuracy with profound implications for our modern world, please subscribe, hit the notification bell, and join our growing community of curious minds. Leave a comment below with your thoughts on space weather or any other historical mystery you would like us to examine next. Your support allows us to continue bringing these verified stories to light. Now, let us journey back to the summer of 1859 and uncover what happened when the sun reached out and touched the Earth. The story begins on the morning of September 1, 1859. Richard Christopher Carrington, a British astronomer working from his private observatory at Redhill in Surrey, England, is engaged in his routine observations. Carrington had been meticulously tracking and sketching large groups of sunspots visible on the solar surface for several days. These dark regions on the sun were particularly active during solar cycle 10, which was approaching its maximum phase. Around 11 o'clock in the morning, while projecting the sun's image onto a screen through a telescope equipped with filters for safe observation, Carrington suddenly witnesses an extraordinary event. Two patches of intensely bright white light erupt from within the sunspot group. The brilliance of these patches rivals that of direct sunlight itself. Carrington watches carefully as the bright areas move and change over approximately 5 minutes before gradually fading away. He makes detailed notes and sketches of the phenomenon. Unbeknownst to Carrington at that precise moment, another observer, Richard Hodgson, independently records the exact same white light flare from his own telescope. Both men document their findings thoroughly. Their independent reports are later published side by side in the monthly notices of the Royal Astronomical Society. This marks the first recorded observation of a solar flare in human history. Carrington is cautious in his interpretation. He notes the coincidence, but does not immediately claim a direct causal link to events on Earth. In his own words, he remarks that one swallow does not make a summer, reflecting scientific prudence. However, the timing of subsequent events would prove profoundly significant. Roughly 17 hours later, on the evening of September 2nd, Earth begins to experience the full force of a massive coronal mass ejection that had been hurled from the sun. This ejection slams into our planet's magnetosphere, triggering an extreme geomagnetic storm. The effects are immediate and global. Auroral displays, normally confined to high-latitude polar regions, become visible at remarkably low latitudes. Reports flood in from around the world. In the United States, the aurora borealis is seen as far south as the Rocky Mountains, where miners mistake it for dawn. In the northeastern states, the light is bright enough for people to read newspapers outdoors at night. Observers in Cuba, Hawaii, and parts of Central and South America witness the spectacle. Southern lights are reported in Australia and New Zealand. The scale is unprecedented in recorded history. The impact on technology, limited though it was in 1859, proves dramatic. The world's telegraph networks, spanning an estimated 125,000 miles of wire at the time, become conduits for powerful geomagnetically induced currents. These currents surge through the long conductors, overwhelming the systems. Telegraph operators report equipment sparking violently. Some suffer electric shocks. In several stations, the induced currents cause fires by igniting paper tapes or wooden components. Service is disrupted across Europe and North America. Contemporary newspapers document these occurrences in detail. The Boston Evening Traveler, for instance, publishes an account of the Boston to Portland line, where operators successfully transmitted messages using only the auroral current after disconnecting their batteries. This extraordinary feat highlights the immense power of the storm. To fully appreciate the significance of these events, we must set the scene of the world in 1859. The Victorian era is in full swing. Queen Victoria reigns over the British Empire. The Industrial Revolution has transformed economies and societies. The electric telegraph, pioneered by inventors like Samuel Morse, represents the pinnacle of communication technology. Messages that once took weeks or months by ship or horse can now travel in minutes along wires. Transatlantic cables are being laid, shrinking the world. Yet electricity remains largely confined to telegraph lines and a few experimental applications. Most households rely on candles, oil lamps, and gas lighting. There are no electrical grids powering cities, no satellites orbiting the Earth, no global positioning systems, and no internet. The world is connected but still fundamentally analog and mechanical in many ways. Solar activity during this period is intense. Sunspot groups large enough to be visible to the naked eye, under proper filtering, have been observed for days. Carrington's observatory work is part of a broader international effort to understand solar phenomena. His documentation of the flare, combined with magnetic recordings at observatories like Kew in London, where Balfour Stewart noted a sudden disturbance known as a magnetic crochet, coinciding with the flare, provides crucial evidence. The following day's geomagnetic storm confirms the connection for many scientists. American mathematician Elias Loomis compiles hundreds of global reports, creating one of the most comprehensive records of any space weather event in the 19th century. These compilations, published in scientific journals, remain foundational sources today. As the mystery emerges through these widespread reports, people react with a mixture of awe and alarm. The auroras are beautiful beyond description, yet their appearance at such low latitudes creates unease. Some interpret the lights as heavenly signs or omens. Others, particularly in scientific circles, begin to piece together the solar origin. The telegraph disruptions add a practical dimension to the wonder. Operators describe their instruments behaving as if possessed. Sparks fly from keys and relays. In some cases, entire stations are threatened by fire. These are not isolated anecdotes but corroborated accounts, appearing in multiple independent newspapers across different countries. The evidence for the Carrington event is exceptionally strong because it occurred during an era of expanding scientific observation and global communication. Unlike earlier undocumented solar disturbances, this one left a detailed paper trail. Magnetometer readings, auroral logs, telegraph company reports, and eyewitness testimonies all align. The storm is now understood to have consisted of two closely spaced major auroral events, with the September 4-2 episode being the most intense, directly linked to the observed flare. Modern analysis of historical data confirms that the coronal mass ejection traveled at an exceptionally high speed, arriving far quicker than typical events. This event did not simply disrupt technology. It revealed a fundamental connection between the Sun and Earth that had been suspected, but never so dramatically demonstrated. Prior to 1859, the idea that solar activity could influence terrestrial magnetism and electricity was emerging but not universally accepted. The Carrington Event provided compelling proof. It helped birth the modern discipline of space weather research, which studies how solar phenomena affect our planet's environment and technological systems. Expanding on the bigger picture, we see how the Carrington Event fits into a larger context of solar-terrestrial relations. The Sun is not a steady, unchanging ball of light. It undergoes cycles of magnetic activity. Sunspots, flares, and coronal mass ejections are manifestations of its dynamic magnetic field. When these eruptions are directed toward Earth, they can compress and disturb our protective magnetosphere. Charged particles stream into the upper atmosphere, creating auroras through excitation of gases. At the same time, rapid changes in the magnetic field induce currents in long conductors on the ground and in space. In 1859, the affected conductors were primarily telegraph wires. Today, they include power transmission lines, pipelines, railway tracks, and undersea cables. The principles remain the same, but the scale of potential impact has grown exponentially with our technological progress. Scientists like Elias Loomis played a key role in documenting the global reach of the storm. His compilations included observations from ships at sea, remote outposts, and major cities. This international dataset underscored that the event was truly planetary in scope. There are, of course, aspects we still do not fully know. While the Carrington Event is the strongest in the instrumental record, we cannot be certain it is the absolute largest possible. Estimates of its energy release rely on reconstructions. The exact frequency of such extreme events is difficult to determine from limited historical data. Paleomagnetic studies and cosmogenic isotopes in ice cores and tree rings offer clues about past solar activity, but they do not provide the precision of modern observations. Questions also remain about precisely how different regions of the modern power grid would respond and how quickly recovery could occur after widespread transformer damage. The voices preserved from 1859 are invaluable. They come from astronomers, telegraph operators, newspaper correspondents, and ordinary citizens. Richard Carrington's careful notes and sketches, Richard Hodgson's corroborating observation, Balfour Stewart's magnetic records, and the many auroral reports compiled by Loomis form a solid documented record. Alongside these, some folk interpretations exist, with people viewing the lights through religious or superstitious lenses as signs of impending judgment or cosmic events. We clearly distinguish between the verified scientific and journalistic accounts and any later embellished traditions. There is no credible evidence of destroyed records or suppression. The event was openly discussed and studied from the outset. Emotionally, the Carrington Event strikes a deep chord. It represents a moment when humanity glimpsed the vast powers of the cosmos intruding upon daily life. The beauty of the auroras inspired wonder and poetry. The disruption of communications brought practical inconvenience and, in some cases, fear. Operators working through the night under sparking equipment, displayed of awe, vulnerability, and human resilience, forms the emotional heart of the story. In our own time, when so much of life depends on fragile electronic systems, that sense of vulnerability feels even more immediate. Looking at where this leaves us today, models and simulations based on the 1859 event paint a serious picture. A comparable geomagnetic storm now could induce currents strong enough to damage or destroy high-voltage transformers across large regions. Power outages could persist for weeks or months, while replacement equipment, which is custom-built and in limited supply, is manufactured and installed. Satellites could experience surface charging, electronics failures, or increased drag from a puffed-up atmosphere. GPS signals might be disrupted, affecting navigation, aviation, and precision timing for financial and communication networks. Undersea cables carrying internet traffic could suffer induced currents leading to outages. The economic cost has been estimated in various studies as reaching trillions of dollars, with long-term societal impacts. Yet this is not a message of inevitable doom. The Carrington Event also demonstrates human adaptability. Telegraph operators improvised and kept lines open where possible. Scientists used the event to advance knowledge. Today, organizations worldwide monitor the sun constantly. Early warning systems exist. Engineers are designing more resilient grids and satellites. Awareness is the first step toward preparedness. Understanding what happened in 1859 equips us to face the next major solar storm with greater wisdom and resilience. The story of the solar storm of 1859 is ultimately one of connection. It connects the fiery heart of our sun to the technological fabric of human civilization. It reminds us that we inhabit a dynamic solar system where forces beyond our control can shape our destiny. As we continue this exploration, we will examine specific modern vulnerabilities, ongoing scientific research, and practical steps that individuals, communities, and nations can take. The Carrington Event is not merely a historical curiosity. It is a critical lesson from the past that illuminates the path forward in an age defined by our relationship with technology and the cosmos. It is a critical lesson from the past that illuminates the path forward in an age defined by our relationship with technology and the cosmos. Building upon the documented events of September 1859, we turn our attention to the deeper scientific and historical layers that reveal how this solar storm reshaped our understanding of the universe. The Carrington Event stands as a pivotal moment not only because of its immediate dramatic effects, but because it bridged the gap between solar observation and terrestrial consequences in a way that previous generations could only speculate about. Richard Carrington's meticulous records provide an anchor for all subsequent analysis. Born in 1826, Carrington was a dedicated amateur-turned-professional astronomer who had already made significant contributions to sunspot studies before 1859. His observatory at Red Hill was equipped with precision instruments, allowing him to project the sun's image safely and sketch features with accuracy. On that September morning, his observation of the white light flare was accompanied by notes on its location within a large sunspot group. The flare's intensity and duration were exceptional. Independent confirmation by Richard Hodgson, a fellow observer, eliminated any possibility of instrument error or hallucination. Their joint presentation to the Royal Astronomical Society solidified the event's place in scientific history. Following the flare, the coronal mass ejection propelled billions of tons of charged plasma toward Earth, at speeds exceeding 1,000 kilometers per second. Upon arrival, it compressed the magnetosphere and triggered intense geomagnetic activity. Magnetometers worldwide registered disturbances far beyond normal fluctuations. At the Kew Observatory, Balfour Stewart recorded the initial magnetic crochet effect, coinciding with the flare's timing, providing one of the earliest pieces of evidence linking solar eruptions directly to magnetic field changes on Earth. This observation was crucial because it occurred in real time, before the full storm manifested. The auroral displays that followed were catalogued extensively. Elias Loomis, an American mathematician and astronomer, collected reports from across the globe and published them in the American Journal of Science. His compilation remains one of the most valuable resources for researchers today. Loomis documented auroras visible in locations as diverse as California, the Caribbean, and Australia. In one notable account from the Rocky Mountains, miners not only mistook the aurora for sunrise, but continued their activities under its light for hours. Similar reports from Havana, Cuba, describe the sky as glowing with a crimson hue intense enough to cast shadows. These low-latitude sightings indicate that the storm injected enormous amounts of energy into the upper atmosphere, exciting oxygen and nitrogen molecules on a planetary scale. Telegraph disruptions provide some of the most compelling technical evidence. The induced currents, known today as geomagnetically induced currents, or GICs, flowed through the Earth's crust and found easy pathways along the long metal wires. Operators in Boston described their keys and sounders operating erratically. In some stations, the voltage was high enough to produce visible arcs and sparks. Fires were reported in multiple telegraph offices, with flames ignited by overheated wires or paper insulation. One station in the American Midwest reportedly burned to the ground after repeated surges. These incidents were not exaggerated folklore, but were reported promptly in local newspapers and telegraph company logs, allowing for verification by historians. A particularly well-documented exchange on the Boston-Portland line illustrates the storm's power. According to the Boston Evening Traveler of September 1859, the operators noted that with batteries disconnected, The line was still energized. One operator tapped out a message using only the storm-induced current, and the reply came back clearly. They continued communicating for some time, marveling at the phenomenon. Similar reports emerged from other lines in Europe. In England and France, telegraph services were interrupted for hours. The event affected both overhead and early submarine cables, demonstrating the global reach of the disturbance. Placing the Carrington event in broader historical context reveals its uniqueness. While smaller geomagnetic storms had been noted before, none matched this intensity or geographic extent in the era of systematic recording. Solar cycle 10 was active, with numerous sunspots observed in the preceding weeks. The flare occurred near the center of the solar disk, an ideal position for an Earth-directed ejection. The rapid transit time of approximately 17 hours suggests an exceptionally fast and dense cloud of plasma. Modern estimates, based on historical magnetometer data and auroral extent, classify the storm as an extreme event, possibly reaching G5 level or beyond on today's scales, though direct comparison has limitations due to differing measurement methods. Scientific progress accelerated in the wake of the event. Carrington and others published their findings promptly. The coincidence of the flare and storm encouraged further research into solar terrestrial physics. By the late 19th and early 20th centuries, scientists like Christian Birkeland and Sidney Chapman built upon these foundations, developing theories of auroral formation and magnetic storms. The Carrington event thus served as a natural laboratory, providing data points that informed decades of subsequent study. Today, it is frequently cited in peer-reviewed papers on space weather as the benchmark extreme event. Despite the wealth of documentation, honest uncertainties persist. We lack precise satellite measurements or modern instrumentation from 1859, so reconstructions of the flare's energy and the CME's magnetic orientation rely on modeling. The exact recurrence interval for Carrington-class events is unknown. Some studies suggest such extremes might occur once every 100 to 500 years, but the sample size is small. Paleoclimate proxies, including carbon-14 and beryllium-10 isotopes in ice cores, indicate periods of high solar activity in the past, but linking them definitively to geomagnetic storms remains an active area of research. Questions also surround regional variations. How would different geological compositions under power grids influence induced currents? How resilient are modern high-voltage transformers compared to 19th-century telegraph wires? Voices from the time capture the human dimension vividly. Scientific observers like Carrington maintained professional detachment while expressing excitement. Telegraph operators described practical challenges mixed with wonder. Newspaper correspondents conveyed public reaction, ranging from scientific curiosity to religious interpretation. Some accounts speak of fear, with people gathering in churches or viewing the lights as apocalyptic signs. Others celebrated the beauty, with poets and artists attempting to capture the spectacle. We distinguish clearly between these documented primary sources and any later unsubstantiated legends that may have grown around the event. The historical record is robust and openly available for examination in archives and digitized collections. The emotional core emerges most powerfully through these personal stories. Imagine the disorientation of miners roused in the dead of night by lights brighter than the full moon. Consider the telegraph operator receiving a shock that sends him reeling, yet returning to his post to keep communication flowing. There is profound humility in realizing that forces generated millions of miles away can reach into our daily lives. In 1859, this realization fostered both fear and fascination. Today, it evokes a similar mix, but with added urgency, due to our deeper dependence on technology. The event humanizes the cosmos, reminding us that we are not isolated on our planet, but participants in a larger, dynamic system. Where this leaves us in the 21st century is a matter of serious consideration based on evidence. Multiple studies conducted by organizations such as NASA, NOAA, and national academies have modeled the impacts of a Carrington-like event on modern infrastructure. Power grids are particularly vulnerable because long transmission lines act as antennas for induced currents. Transformers can overheat, saturate, or suffer permanent damage from GICs in the tens to hundreds of amperes. Replacing large power transformers takes months or years, and global manufacturing capacity is limited. Widespread blackouts could affect hundreds of millions of people, disrupting water treatment, hospitals, transportation, and food supply chains. Satellites in low Earth orbit would face increased atmospheric drag from a heated and expanded thermosphere, potentially leading to orbital decay for some spacecraft. Electronics on board could suffer from surface charging and single-event upsets caused by high-energy particles. Communication and navigation satellites, including those in the GPS constellation, could experience outages or degraded performance. The Internet, reliant on undersea fiber optic cables and data centers, might suffer cascading failures if landing stations or power supplies are affected. Aviation would face challenges with disrupted GPS and radio communications, forcing reliance on backup systems. Economic assessments vary, but converge on enormous potential costs. One often cited analysis estimates trillions of dollars in damages for the United States alone, with recovery taking weeks to years, depending on the severity and preparedness. These projections are grounded in engineering simulations and historical analogies rather than speculation. Importantly, not every Carrington-level storm would produce identical outcomes. The orientation of the magnetic field in the CME plays a critical role in determining impact severity. Fortunately, awareness has grown. Space weather forecasting has improved dramatically. Satellites like SOHO, SDO, and ACE monitor the sun continuously. Agencies issue alerts when major flares or CMEs are detected. Grid operators can take mitigating actions, such as adjusting power flows or temporarily disconnecting vulnerable lines when warnings are received. Satellite operators have procedures for safe modes during storms. International collaboration through bodies like the International Space Environment Service coordinates global responses. Individual and community preparedness also matters. Understanding that solar storms are a natural hazard alongside earthquakes and hurricanes encourages practical steps. Maintaining emergency supplies, having non-electronic backups for critical information, and supporting investments in resilient infrastructure contribute to overall readiness. The Carrington Event teaches us that while we cannot prevent solar activity, we can reduce its consequences through knowledge and planning. As we reflect on the full scope of the 1859 storm and its modern implications, several key takeaways emerge. First, the sun is the ultimate driver of space weather, and its power dwarfs human technology. Second, historical events provide essential calibration points for risk assessment. Third, scientific openness and international data sharing, as exemplified by Loomis's compilations, remain vital. Fourth, human ingenuity in the face of disruption, seen in the telegraph operator's improvisation, offers inspiration. The legacy of the Carrington Event continues to influence research. Recent studies using advanced modeling techniques simulate how a similar storm would propagate through today's interconnected systems. Papers published in journals such as Space Weather and Geophysical Research Letters analyze vulnerabilities in specific sectors. Historical research digs deeper into archival records, uncovering additional eyewitness accounts that refine our picture of the event. In conclusion of this segment, the solar storm of 1859 stands as both a warning and a beacon. It warns us of the fragility inherent in complex technological societies. It beacons us toward greater understanding, preparedness, and humility before the forces of nature. By studying this true historical event with rigor and respect for the facts, we honor the observers of 1859 and equip ourselves for whatever the sun may send our way in the future. The Carrington Event reminds us that the universe is alive with activity. Our sun pulses with magnetic energy. Coronal mass ejections are a regular feature of solar behavior, though extremes like 1859 are rarer. Continued monitoring and research are essential. Public engagement with these topics fosters informed support for scientific endeavors. As we advance into an era of increasing solar maximum activity in the coming years, the lessons from 1859 grow ever more relevant. Expanding further on potential modern scenarios, experts note that simultaneous impacts across multiple sectors could create compounding challenges. A prolonged power outage combined with satellite disruptions could hinder emergency response and recovery efforts. Supply chains for replacement parts might be strained if global communications are affected. However, redundancies built into many systems, along with rapid response protocols, could limit the duration of some outages. The key lies in proactive hardening of critical infrastructure, something that is already underway in several countries. Stories from 1859 also highlight societal resilience. Communities came together to share information through alternative means when telegraphs failed. Families and neighbors relied on direct human communication. These examples suggest that while technology amplifies both our capabilities and our vulnerabilities, human connections remain fundamental. In a future major solar storm, such social cohesion could prove invaluable during recovery periods. Scientific institutions continue to study analogs to the Carrington Event. The 1989 Quebec blackout, caused by a smaller geomagnetic storm, provides a more recent case study. In that event, a rapid collapse of the Hydro-Quebec power grid left millions without electricity for hours. Transformers were damaged, and recovery took time. Scaling this up to Carrington levels illustrates the potential severity. Other historical storms, such as the 1921 event, also offer insights, though none match 1859 in documented intensity. Ongoing research explores ways to better predict and mitigate risks. Machine learning models analyze solar data for better flare forecasting. Engineering solutions include GIC blocking devices for transformers and improved satellite shielding. International agreements facilitate data sharing and coordinated responses. These efforts represent the positive legacy of events like the Carrington storm, turning potential disaster into opportunities for advancement. As this exploration draws to a close for now, we recognize that the full story of the Carrington event and its relevance today encompasses science, history, human experience, and forward-looking strategy. The verified facts ground us, the open questions humble us, the emotional resonance connects us across time, and the practical implications urge action. The sun will continue its cycles, major storms will occur again. Our response, informed by the past, will determine the extent of their impact on our future.